So good evening one and all. We are going to discuss about the problem of estimating power spectral density of a wide sense stationary random process. Power spectrum is actually obtained from the Fourier transform of autocorrelation sequence. Therefore, estimating the power spectrum is equivalent to estimating the autocorrelation. For an autocorrelation ergodic process, we know that it is obtained from this formula. It is called autocorrelation ergodic time average autocorrelation formula. If x of n is known for all values of n, estimating the power spectrum is a straightforward problem. So what you should do, you have to determine the autocorrelation sequence and then you have to compute Fourier transform. So what are all the difficulties in this approach? Because still spectrum estimation is found to be a challenging problem. The amount of data that one has to work with is never unlimited, and in many cases it may be very small. Such a limitation may be an inherent characteristics of a data collection process in quite a few examples, such as the analysis of seismic data from earthquake, in which the signal persists only for a short period of time. It is also possible that a limited data set is imposed by the requirement that the spectral characteristics of the process remain constant over the duration of the data record. For example, in speech processing applications, a stationarity requirement will restrict the length of time over which the signal may be assumed to be approximately stationary, probably for a few milliseconds or less than that. The second difficulty is that the data is often corrupted by noise, contaminated by an interfering signal. So spectrum estimation is a problem that involves estimating px of e power j omega from a finite number of noisy measurements. In some applications, spectrum estimation is done using a priori knowledge about the process, how the process is generated. For example, if I know x of n, that it is an autoregressive process, that it consists of one or more sinusoids in noise, this type of information may then allow a person to parametrically estimate the power spectrum, parametric power spectral density estimation. Sometimes to extrapolate the data, sometimes it's autocorrelation in order to improve the performance of spectrum estimation algorithm. So there comes a question, what are all the applications of spectrum estimation techniques? For example, in the case of Wiener filter, smoothing filter, before it is to be designed and implemented, the frequency response of a non-causal Wiener filter will be given by h of e power j omega, which is equal to PD of e power j omega divided by power spectrum of d of n, PD of e power j omega, and power spectrum of the white noise. So power spectrum of the d of n, power desired output of the Wiener filter, power spectrum of the noise v of n must be known to work with non-causal Wiener smoothing filter. Therefore, before a Wiener smoothing filter operation is designed and implemented, the power spectrum of both d of n and v of n must be determined. So these power spectral densities are not generally known a priori. They are not available a priori. We need to estimate from measurements. Another application with the problem of estimating measurements. For example, it plays an important role in signal detection and tracking. A sonar array is placed on the ocean floor to listen to the narrowband acoustic signals that are generated by the rotating machinery or propellers of a ship, whether any ship arrives or not. Once a narrowband signal is detected, the problem of interest will be to estimate its center frequency in order to determine the ship's direction as well as velocity. Complete sonar array operation is implemented. Shown narrowband signals that are typically recorded is in a very noisy environment. on the ocean floor. Signal detection, frequency estimation are non-trivial problems that require robust, high-resolution spectrum estimation techniques. Would you agree with me or not? So, signal detection and frequency estimation in a noisy environment, such as in case of sonar array which is on the ocean floor, to know about the narrowband signal and estimation of center frequency, is a non-trivial problem that require robust, high-resolution spectrum estimation techniques. Some more examples can be given like this: harmonic analysis, harmonic prediction, time series extrapolation, time series interpolation, spectral smoothing, bandwidth compression, beam forming, hybrid beam forming, direction finding of arrival of incoming signals, what not. N number of applications are available. Normally, there are two approaches for spectrum estimation. First includes classical and non-parametric method that begin by estimating the autocorrelation sequence from a given set of data. Power spectrum is then estimated by Fourier transforming the estimated autocorrelation. It is called non-parametric approach. Whereas the second class of spectrum estimation, it is called non-classical parametric approaches, which are based on using a model in the process in order to estimate the power spectrum. If it is known that X of n is a pth order autoregressive process, then the measured values of X of n may be used to estimate the parameters of the all-pole model, AP of k, and then the estimated model parameters AP of k cap may then be used to estimate power spectrum as given in the equation. So, let's see the non-parametric models in general, non-parametric techniques of spectrum estimation. These methods are based on the idea of estimating the autocorrelation sequences of a random process from a set of measured data, X of n, observed data, and then taking the Fourier transform to obtain an estimate of the power spectrum. Periodogram, non-parametric method, was actually introduced in the year of 1898 by Custer in the study of periodicities in sunspot numbers. The periodogram is very easy to compute, but it is limited in its ability to produce an accurate estimate of power spectrum. Periodogram is identified as a shortcut method, easy to compute. It is limited in its ability to produce an accurate estimate of the power spectrum. Why? Because when it is applied on short data records, finite length data records, we have to confirm that periodogram converges to power spectrum. Let's see one after the other.